Hello, this is a review of Unit 2 for your final exam for ENGR 201. For this one, remember it's partial derivatives, and here we're trying to use the chain rule in order to calculate certain components from this equation. So it says find the partial of u with respect to x in general terms. So this means the overall chain equation or chain rule. So we have partial of u with respect to x. So with that, remember u is our overall function with w, x, and y, and z in it. So it's going to be, so we'll go by w first. So you always need fw and then the partial of w with respect to x. So you need to have your term with respect to the function and then your variable with respect to whatever you're taking the derivative of. And now plus we have x, so it's going to be fx, and since we're taking it with respect to this partial with respect to x, it's going to be partial of x over partial x, which you can just write as just fx if you wish, because this goes to 1. And then plus fy, partial of y with respect to x, plus fz, plus the partial of z, plus fz times the partial of z with respect to x. Alright, so now we need to find partial of u with respect to x while holding while holding y and z constant. So with finding this, you need to look towards using your constraint for part of it, and look towards using your function for the other part. So you use your function to find terms like fw, fy, and then you use your constraint to find terms like partial of y with respect to x and stuff like that. So in this case, we're holding y and z constant. So we're holding y and z constant. Let's go ahead and write down that general equation. So what we're looking for. So this will equal, so we're holding y and z constant, that means fw, partial of w with respect to x, because these are considered not constants. They're dependent upon x. Now plus fx. Now this is all we need, because partial of y with respect to x is then 0, as well as partial of z with respect to x is 0, because again it's like taking a derivative of a constant with respect to x. So all of this right here is just 0. So we calculate fw, and then this right here is technically the partial of w with respect to x holding y and z constant. So fw, you get that from your function u. So fw would then be, so we take derivative of that first term, cosine wy, which would just be y minus sine wy, plus take derivative of that whole. So since we have a function of x and w together, we're not holding, because we are holding y and z constant, but again, x is a little different. Oh, I forgot to mention. When we take the derivative of, wait, no, we're fine. Never mind. So now we take the, ignore me. Again, we're still just finding fw. I forgot we're not finding the partial w with respect to x yet. So now this is going to be, we're going to hold x squared, y, and z constant, because again, we're finding fw. And we have y plus times z. The last term doesn't have any w's in it, so it goes to 0. We want to find fx. That first term doesn't have any x's in it, so it goes to 0. And then the second term, the wx squared yz, that has an x in it, so it becomes 2x times w times y times z. And then the second term has an x in it, so the derivative of the inside is going to be z times the derivative of sine xz, which is going to be cosine xz. So now the hard part is going to be calculating the partial of w with respect to x. So there's two ways you can go about it. But you can either use the implicit function theorem, or you can solve it implicitly. For this first one, I'm going to solve it using the implicit function theorem, or let's see which one I have more space on. They're about the same. So I'll go ahead and solve for the implicit function theorem first, and then the next one I'll solve implicitly. So if I'm using the implicit function theorem, then I need to set this equation right here equal to, since it's already equal to a constant, I could then say this is now equal to some g of x, w, y function, because this is essentially a function of g. Sorry, this function of g is of x, w, and y. So now if I want to find the partial of w with respect to x, holding y and z constant, I can set that equal to then g, so negative g prime, negative g sub x over g sub w. So this is going to be partial derivatives with respect to x and partial derivatives with respect to w. So this first one with respect to x will then be, this would be 2w squared x. Again, so I'm starting right here. Plus, this is going to be wy. And this last term is going to go to 0. And now over gw, so again, we're starting here. So it's going to be 2w x squared. That term has a w, so it's going to be plus xy. The last term does not have a w, so that goes to 0. So this is essentially the partial of w with respect to x, holding y and z constant, using the implicit function theorem, which again is the partial of whatever's in your denominator and the numerator over whatever's in the numerator and denominator. That made no sense, but just memorize the equation. It's in the review. So now we need to plug all these terms in for that equation that we started off with. So all these just go into these respective components. So then we're left with partial of u with respect to x, y, z, then becoming fx, which is in negative y sine wy plus x squared yz times the partial of w with respect to x holding y and z constant, which is the negative 2w squared x plus wy over, you keep parentheses on that, 2wx squared plus xy, and then plus fx, which is then 2x wyz plus z cosine xz. All right. So now we're being asked to find the partial of u with respect to x, but instead of holding y constant, we're holding w and z constant. So our overall equation is then going to become, set of fw is going to be fy times the partial of y with respect to x, then plus fx. And again, this partial y with respect to x is going to have w and z constant in that notation. The other terms, they go to 0 because, again, they're held as constants. So this first one, fy, again, let's look back up here. We need to, I want to solve for fy up here so that way you can follow my path. So fy is going to be the derivative of that first term with respect to y, which is going to be w sine, negative sine wy plus w x squared z. And the last term goes to 0 because it has no y's in it. So now we have fy to be negative w sine wy plus x squared wz. So now we need to find the partial of y with respect to x, holding w and z constant, because we don't need to solve fx again. We already solved that right here. So we don't need to solve that again. So now last time I solved it implicitly. Last time I solved it using the implicit function theorem. This time I'm going to solve it using I'm going to solve it implicitly. So I want to go ahead and write down that equation right there. W squared x squared plus wxy plus y squared equals 5. All right, so when you solve it implicitly, remember just back to Calc 1. Every time you take a derivative of whatever your dependent variable is, in Calc 1 it was y. In this case, it's also y. You're gonna have a y prime term. In this case, our y prime term is gonna look like that, the partial of y with respect to x. So now when we solve for this first one, this is gonna do a big partial with respect to x, holding w and z constant. So this is applied to the entire thing and this side, but this side is also, this is going to just go to 0. So now we need to take the partial of each term. So the first term, we have w and x squared, so that's w is like a constant. So it's going to be a partial of x squared, so it's 2x w squared. Now this next one's going to has a function of both x and y. So we're going to have a product rule applied in order to calculate this, because when we take the partial of x, it's going to be there's no residue, but when we take the partial of y, then we're going to have one of those extra terms. So again, do partial of x first, so we can have wy, then plus the partial of y, so it's going to be wx, and then we're going to have a partial y with respect to x. So I'm going to leave it like that. And then lastly, we have partial of y squared, so it's going to be like normal, 2y, but then we're going to have the partial of y with respect to x equals 0. Because again, we're taking the partial of 5 with respect to x, which is a constant, so it goes to 0. So now our next step is to isolate these terms here, so we can factor out the partial of y with respect to x. So now I'm going to move all the other terms to the other side. So we're going to have a 2xw squared plus wy equals negative wx partial of y with respect to x minus 2y partial of y with respect to x. I'm going to move this over here so I can have more space. So now I'm going to I want to factor out the partial of y with respect to x. So I want to make this just equal partial of y with respect to x times negative wx minus 2y. And then I can divide this term to the other side, leaving we have partial of y with respect to x, holding w and z constant to equal 2x squared w plus wy over negative wx minus 2y. So either method is fine if you like to use implicit versus implicit function theorem. I prefer the implicit function theorem because it's quicker and less algebra. But if you don't like using that function, that theorem for whatever reason, I totally get it. It seems like magic to me. So just go ahead and plug into this function. So now, again, we're plugging back into up here. So that means that our partial of u with respect to x, holding w and z constant, is going to equal fy, which is this term, the negative w sine wy plus wx squared z, all times by the partial of y with respect to x. So that's going to be 2x squared w plus wy over negative wx minus 2y. And then plus fx, which is again back up here. I'm just going to write it right here. Plus 2x wyz plus z cosine xz. So then this is that. Now lastly is to find the partial of u with respect to x while holding w and y constant. So the reason why, and so this will become undefined, because when we look back at our constraint, this right here, I want to copy this and bring it down and show you why it's undefined. So this function, this constraint here is to show that if some of the functions are, if say y and x were dependent, that means that w would then become the independent variable. So it just shows that all the combination of these, the w, x, and y, they have to come out to being 5 on this constant. And if they're all considered simultaneously constant or independent, like, so when we have the partial of x here, that makes it independent. When we have this w here and this y here, we say w and y are constant, but what we really mean is that they're independent of x. X can't control it. The partial of w with respect to x is just going to be 0 because there's nothing that constrains it to being a part of x. So if w, x, and y are considered all independent of each other, then there's nothing that's going to hold them to this constraint. It just can't happen. It's like saying that when you add up something, like you say you have 3 things together and they're supposed to add up to 5, but instead they can be whatever they want, and then you can just, and you're trying to say, well, I have 10 of one thing plus 5 of another plus 6 of another, and that's 21 and not 5. So that's what, like, if they can all be what they want, or they can all be independent of each other, then this constraint will not hold. Then there's nothing that says that w, x, and y combination has to equal 5. So this is why this is considered undefined. Whoa. So what you would say on the test precisely is undefined because x, w, and y cannot be simultaneously independent. All right, no, my handwriting's bad, but that's why I'm saying it, so you at least know what I wrote. So that's a good. This is the review of Unit 2. This is everything you could possibly need to know for Unit 2 in terms of partial derivatives. Good luck on your test. I hope this helps.